Hello, and thank you for joining me to understand the most rudimentary aspects regarding point defects and dislocations. So in this lecture, we will introduce to you the most common types of defects, aka crystal imperfections that may take place in crystalline solids, and we will distinguish between different types of defects. So essentially, we will label them either as point defects or extended defects. And we will then provide a simplistic model to explain the discrepancy between the simplistic model we covered in the previous lecture and the measured yield stress values, shear stress values that were seen to be so much off with the prediction based on the simple model. And please recall that the elastic properties, they are interrelated. So even though we might be more interested on the yield stress value when we are looking at the stress strain curve, looking into also the shear stress, and the yield shear stress does provide us an order of magnitude approximation. And finally, if I recall correctly, we will also speak a few words about work hardening, which is a process that can be used to modify the extent of regime, like elastic deformation regime of a material, provided that we can perform work hardening on the material. So these are the things that we will be covering in this lecture, and I will start by first just giving a brief motivation slide on defects and dislocations. So lattice defects, and they're also known as crystal imperfections. In general, they are very important in solid state physics and also in other branches of physics. So in photonics and optics, we are also many times interested in crystal imperfections in the end. Some examples are, if you're interested on the electronic properties of solid state systems, we could come up to look into quantum dots or quantum well structures and what they are in a nutshell. They, for example, can be used to be nanoscale emitters of light or absorbers of light. So essentially, they are structures, quantum mechanical structures, where we very intentionally we break up the band structure of a solid and give rise to defect states. And this can be used, for example, when we want to dope semiconductors. We can do like you play around with these kind of tricks, or we can make light sources, and there's lots of things that can be done with these structures and these concepts that are related to lattice defects. Another example, photonic crystal waveguides and photonic crystal cavities. My apologies if you don't approve that I'm also speaking of something from my own field of expertise. This is a prime example, photonic crystal structure of the math that is being utilized, that is related to lattice defects and crystal imperfections. So this is exactly an example application that we use in optics and photonics, and it's based on the first principle work performed on solid state physics. Then more related to solid state physics, we can also look into the conductivity of metals, and this is what we will do later on in our chapter 5, and we will learn that the defects, crystal imperfections, grain boundaries, and these things, they do limit conductivity of electrons when we are looking at macroscopic objects. So that the conductivities of metals, for example, is very highly affected by lattice defects. Another example, and this we will we will bump into this even faster, when we look into the thermal properties of solids, and this we will be focusing on in chapter 4, we will learn that lattice defects are actually quite important when we are also looking at thermal conductivity of materials. And diamond, for example, is a prime example of a material system, or silicon or germanium, where it's the lattice defects, the crystal imperfections, and that play a huge role in the thermal conductivities of materials. And it goes even to a stage that if one wants to maximize the thermal conductivity of your material, for example, the diamond, you really want to even purify the diamond to be isotopically pure diamond so that it doesn't have a different isotopes of carbon on it. So they kind of the lattice defects and these kind of how pure materials we want to come up with. Like things become like very sensitive. Like for example, the thermal conductivity, it becomes very sensitive in the end on lattice defects when we want to kind of like achieve the state of the art performance out of our material. This is a better way of saying it. So when we go to the kind of like a state of the art, when we want to achieve ultimate performance out of your material, then we end up often of trying to eradicate lattice defects. So this is my brief motivation that it's actually very important, and it's not related. These defects and dislocations, they are not only related to this chapter, but they are very, very much related to research on solid state physics in general. So please take this seriously. This topic we will be covering next. So there's these lattice defects, and roughly they can be divided into two different categories or labels. So first of all, there are point-like defects, and we call them point defects, and they are localized. So essentially it's a point-like deviation from the ideal crystalline lattice. And that can be described mathematically with the Bravai lattice and just placing like the basis of the like lattice into each of those lattice points. And then we have extended defects, and these are not point-like defects anymore, but rather larger in dimensions, so extended perturbations and deviations of the lattice. And this is, I'm highlighting this schematically, that what extended defects may be. For example, this would be a piece of a two-dimensional material. So for example, just a single flake of graphene. And then when we go to large enough flakes of graphene, no flake of graphene, even though it might be just a single flake thick, like single atomic layer thick, when we move in X and Y directions along the plane of the flake, there will be some grain boundaries where the crystalline structure of graphene will be changed into slightly different. And then because of this, we can, for example, try to see that when electrons would try to be moving around in this flake of a 2D material, when the electron sees this boundary, it may not just go directly through, but rather it will be scattering a little bit in here. And this is some example of an extended defect. more on those later in this lecture. Let's look first into the type 1 defects, so these point-like defects. And I will show you a picture that will hopefully clarify what kind of point defects we may have in our atomic lattice. So we may have these interstitial atoms. So it's the same atom, but it's in a different location, that not in the location of the atomic lattice. And we could also have a different atomic isotope, and that would give rise to these kind of defects. We can have a vacancy site, so we would have a point in the lattice where we should have an atom that we don't have an atom anymore, and this is one type of a defect. Then we may have either substitutional smaller atom, so that we will replace a single atom in the lattice with something smaller, a replacement atom, and then we will also may be able to, or sometimes it may also happen that we have a larger atom that is being substituted in terms of a original atom, and then we may have a defect, which is actually a combination of two defects, and these are, for example, called Frankel pair. So that we have a vacancy, and that it's being combined with interstitial atom, and these two pairs they form a kind of combined defect. named after its inventor, Frenkel. So this is some examples. These are some examples of point-like defects that may take place in a ideal crystalline lattice. And remembering that the lattice constants of crystals there are the order of like a nanometer angstroms. So in a, for example, 1 centimeter cubed sized solid, we will have a huge number of atom lattices. So even though we have a very pure material, we cannot purify materials into arbitrarily pure states. So we will always have some impurities of other materials, other substances in our piece of a solid, and we will also have different isotopes of the same solid, same element present, and these things will ultimately play a role in the properties of the materials. Kittle's book has a very good description on defects and lattices, so that they please read about, like read from Kittle more. And Ashcroft it is also, I think, was mentioning defects in more depth. So point defects, these are some of the examples shown in the figure. And what they are, for example, interstitial defects are often used to improve the mechanical properties of alloys. So this is an example where we are actually taking use of intentionally adding defects into our material. And like a good example of an alloy is carbon steel, where we add a little bit of few percents of carbon into iron and we make steel. And the mechanical properties of iron will be improved dramatically when we add intentionally a given amount of carbon into the structure. Somehow, like it makes the whole atomic structure more rigid in terms of plastic deformations. We may also have substitutional defects, and these can be used to change the properties of materials. Especially, I'm thinking here. I'm thinking of doping of semiconductors, and then I could change the conductivity of my semiconductor by just changing the amount of substitutional defects. So essentially, I'm introducing dopants into the semiconductor intentionally, and that will change the conductivity of the semiconductor, and then that will also change the type. Like depending on the type of doping, I can make a p-typed doped semiconductors, I can make n-typed doped semiconductors, and then I can actually make semiconductor junctions. And with semiconductor junctions, p-n junctions, I can make a diode, and if I can make a diode, I can also make a transistor. So p-n-p diodes, for example, and then if I can make a transistor, I can multiply that. I can make many transistors, and then I can actually make electronic devices based on semiconductors. And all of these things are really based on being able to dope semiconductors accordingly. So we are really in intention, we are adding defects into the semiconductor structure, and that will dramatically change the properties of the materials. So these are just some examples. Then we have these extended defects, and here, like a grain boundary is a good defect to remember as a term. So we have like for example in 2-dimensional material and also in 3-dimensional material, we have parts that are ideal, crystalline and monocrystalline, but the actual solid, the macroscopic solid, is a polycrystalline piece of a solid. So it's being formed out of many monocrystalline pieces of volumes. And then when we put these different crystalline volumes together, there will necessarily be grain boundaries, and they will affect the properties of the materials. They will affect the electronic properties. So it's clear to understand that electrons may not propagate through the solid as nicely when we have grain boundaries present, but also the thermal conductivity will be decreased because we will have grain boundaries that quite seriously disrupt the propagation of phonons. So these are the things that come to my mind first when I'm thinking of grain boundaries. Dislocation is another type, and this will be covering in here in more detail, and they are quite important. So this is shown in the figure that we actually have an extra sheet of atoms here, and this is causing a change in the atomic structure, in the crystalline structure of the material, and it's not a point-like defect anymore, but rather we have an extended defect here. We have an extra sheet of atoms that is then deforming our structure. And here, this can be, we can define a slip plane with respect to the kind of extra sheet of atom that here on the left-hand side of the slip plane, we still have the ideal crystalline solid. And then on the right-hand side, we have the modified deformed crystal. So these extended defects, they are abrupt irregularities in the lattice. And what they do in the context of this chapter, they explain the plastic behavior of solids. They also explain thermal and electron transport properties of many solids, so that it's not just that they explain why plastic behavior takes place in materials. And it's not just that they explain that why yield stress values are lower in practical materials than what the simple theoretical arguments suggest. And maybe I will have a homework on Creep, because that was a good song. Sorry about that. But it still is a good song of a kind, yeah. But as an example of these properties, but I don't know, who knows. Joke ends here. I will go forward. I don't have a homework on Creep. Or maybe I will, I don't know. I'm not sure. What next? So now we are ready to understand, at least on a qualitative level, what happens when the solid turns from a elastic solid to a plastic solid. And we can understand the transition from the microscopic point of view, and how come it happens so much easier in realistic materials than what the theory predicts. So we want to understand the huge discrepancy between the measured and the estimated yield shear stress values, as we encountered in the previous lecture. And we consider a crystalline solid that exhibits an edge dislocation, and we will have a subsequent slip plane, and this is shown in the figure below, so that we will have the edge dislocation here, and we will have a slip plane. And this is what can be used, this kind of a picture is what can be used to explain why shear stress can take place and can deform realistic solids so much easier than what we could imagine should take place in ideal crystalline structures. So what happens here is that because there is this kind of a defect there, is that the atoms can now glide from one lattice side or lattice column at a time. So please look at the figures from A to C to kind of see what I'm trying to say here. And basically, like from this location, how this defect side can be seen to move to one step rightwards is that we break two bonds, and then this plane can move along here and form two more bonds. Or sorry, just like we break two bonds, and then we form a new bond here. So we just like move this slightly. And now the defect is seen to be moved, and we can repeat the process. So like we can essentially one column at a time, we can displace, we can move the defect aside. And what happens after a while, we realize that now with respect to the slip plane, what happens is that these atoms are and this plane is actually now moving with respect to the upper part of the material. So in essence, we see that the material is being sheared. And the thing that is now important, that instead of like all the planes moving one at a time at the same time in the macroscopic material, now this shearing, this deformation can happen like a one atom or one atomic column at a time, or a smaller number of atoms at a time. And that means that we will have less atoms at a given time interval that need to move, and this means that less shear stress is actually needed, and less energy is needed to be able to change the atomic structure. And this is the explanation that explains the huge discrepancy between the theory and experiments. And edge dislocations are actually quite common in materials, and this is most of the time the mechanism, that process that dominates in realistic materials. And this explains the low experimentally measured values for the yield shear stress sigma y. And if I remember it correctly, experiments have been made on ultra pure materials that do not have edge dislocations and don't have that much of defects. And what the experiments have shown is that the experimentally measured yield shear stress values actually exceed when we have more ideal structure. So that this really complies quite nicely with this qualitative description we have here. So physically, the yield shear stress value sigma y corresponds to the stress, which is enough to translate a single or a few dislocation lines at a time. So bones are being broken down and reformed one atom or one column of atoms at a time. And either way, like we can either see this as a movement of dislocations, or we can see this as a movement of atomic columns. In the end, it doesn't really matter. And this is the simplistic but quite valid understanding that provides us the methodology to also increase the yield shear stress values if we would wish to do that. So somehow, if you would want to come up with materials that would not be sheared that easily, we could, based on this simple description, we could conjecture that we need to somehow reduce the possibility of atoms to move. So we need to hinder the movement of dislocation somehow, and this should affect the yield shear stress values of materials. And this is actually what happens when we would do these kind of like a material development. And this is achieved often by really introducing new defects into the solid intentionally. So for example, recall the carbon steel, where we are intentionally adding carbon to make harder steel. So for example, like adding interstitial defects, we can lock down the structures, because then the atom columns, they cannot move like single column at a time anymore, but rather many bonds need to be broken down and reformed in a given time interval. And that requires more energy, and that makes the process less probable to take place. And like I said, this is an approach that can be used to harden materials. So for example, the carbon steel. And basically even a small few % amount of carbon impurities can really visibly change the mechanical properties of steel. And this I really recommend you to read from Wikipedia on how things work in practice, but it's a very tangible and hands-on example of this kind of considerations. And very quickly we moved into the science of metallurgy when we are looking at these different concepts. And then we also realize that very quickly we wannabe solid-state physicists end up talking with people who are not physicists at all, but rather they are actually like engineers, and they have like real tangible problems they want to solve, and then we may be able to help them in their issues. And then then we are usually quite happy because we can actually benefit the mankind, or at least we can dream that we can benefit the mankind. So okay, and unlike how the process happens is that we have vacancy defects, and the vacancy defects, dislocations, they enable atoms to move one atom column or one atom at a time, and this is what makes the materials softer. And if we fill up these vacancy defects by impurities, this is a mechanism that can be used to harden materials when we are looking at the microscopic description of things. And this is what was shown in the figure earlier in the final D part, and now I'm repeating that. So when we are intentionally adding a impurity here into the place of a vacancy site, we see that the atoms can no longer move, and this is really the mechanism on a microscopic scale that explains what happens on a macroscopic scale. For example, how can we harden steel by just adding a few % of carbon into the metal? So sometimes we can add defects, and it's a good thing. It improves the properties of the material, and then sometimes it's a very bad thing, and we want to purify the material. So it's really a matter of taste and a matter of application, which way you want to go. And the final region to consider in the plastic deformation regime is in the stress strain curve is this region of work hardening that has been shown schematically in the region that highlighting in the figure in blue. So like here, like if it's not very visible, we have the elastic region, and after yield stress value has been exceeded, we have the easy glide region where we are like easily straining the material, and then we encounter this kind of steeper hill. This region is called the work hardening region. And why it's called work hardening region is that we can look that if we increase the applied stress of our system, and when we have moved here, like we are in the plastic regime, and when we turn the applied stress off, like we no longer return to the original dimensions of the solid, we no longer return to this 0 point in the stress strain curve, but rather we go somewhere downwards, somewhere here. So that we do not anymore get into the regime where we have zero strain. And this of course physically means that the length of the solid has been changed. And the kind of what happens then for the stress strain curve is that we may end up in a situation that we now have a new elastic regime in our material, and we now may have a larger value of yield stress value that the material can take before the elastic regime is being moved, before we move beyond the elastic regime. And this is sometimes an important thing, because we can harden the material, because the material does no longer go into the plastic regime as easily, because we can increase the original yield stress value to the changed yield stress value. And this is quite important to know, like depending on the applications. Sometimes you need to acknowledge this, and sometimes you harden your material in advance so that the dimensions of the material remain more controllable when they are being, like when forces are being applied upon the material. And the terminology goes that the recoverable amount of strain that we call epsilon E, and that's the elastic strain. And that's shown in the figure that this is the amount of strain that is still recoverable. So this is the new elastic region in the material in practice. And then we have this rest of strain, and that's called plastic strain, epsilon P. And this is the not recoverable part of the strain. So this is a bit of terminology for you to know. And this is roughly the process of work hardening. And sometimes this is quite useful because you can really change, you can improve the properties of the material. in essence, you can harden it down by doing these kind of tricks. And then this is what I wanted to say in this lecture. I thank you for following me for this half an hour. And please, in the next lecture, we will go to the role of defects in plastic deformation. No, this is already that part. Okay, sorry. We will go to fracture in the next lecture. Thanks and bye-bye.